This is a first of all, spontaneous process, which leads us to a free energy, delta G, to be negative or less than zero. And we recognize this process in general as the use of chemical reactions to produce electrical energy. And certainly one area of research that's very active is the process of manufacturing batteries that have extended lifetimes and can deliver charge at a reasonable power level. And this is one of the biggest stumbling blocks to the electric car, if you will. And while we're still buried into petroleum uses, the efficiency, that is, of use is so much greater for a long period of time using petroleum and internal combustion than it is for batteries and so forth like that. But I figure by the year 3052 that we'll figure it out. Anyway, for all practical purposes, we'll just do the basic concepts. If you'd like to unlock that, just flip that, close it. I think we're all good. It's the other way. There you go. And keep it flopping. Anyway, to deal with this, you have to understand when we talk about galvanic process, we're talking about coupling two oxidation reduction type reactions. And just the one I'll use for the most part is copper plus a couple of electrons goes to copper solid, and then we'll have zinc plus zinc metal, excuse me. Yeah, zinc metal will go to zinc plus 2 plus a couple electrons like this. Well, again, we have a reduction process and an oxidation process. And again, we have to balance the charge and mass, and so the net cell reaction for this will show up in this context. In order to construct a battery, which is a sustainable delivery of electric charge, you have to separate the oxidation reduction processes. What you have is two issues taking place from this one process, as I'm showing you here. You have an uncontrolled galvanic process, and a controlled. In order to generate a sustainable delivery of electric charge, you have to, of course, have a controlled galvanic process. And in this process, the oxidation reduction processes are separated by what I will explain to be a salt bridge. Now, there are other separations in galvanics that we're not going to get into, but the purpose of the salt bridge is to maintain a balance of charge, and we'll explain as we go through this. But I want to show you the issue in the uncontrolled galvanic process so you can appreciate the separation and the setup of the control issue. Let's take, for example, a solution of copper sulfate. Like this, and what we're going to do is we're going to insert in that solution a zinc bar right there. The reaction that I showed you up here will initiate spontaneously. The zinc will begin to undergo oxidation and dissolve, start dissolving into solution. Right here. The copper will pick up the electrons from the zinc, and copper will begin to precipitate, come out in a reduced form. Well, where does the copper go? Well, the copper starts depositing on the zinc surface. And over time, there builds up such a layer of copper on this that it blocks access of zinc for that, of copper ions to that surface. So in this case, when the copper coating reaches a certain point, it will stop the oxidation reduction process. This doesn't take long. So the essence of this is that you have an uncontrolled process, and the charge flow, the electron charge flow for oxidation reduction, is not sustained for very long periods of time. It's a result of the bar getting coated out by the copper and forming a barrier between the zinc trying to undergo oxidation and the copper undergoing reduction. So reaction stops after a short period of time. On the other hand, if we separate the oxidation reduction reactions, we can generate a sustained flow of electric charge, and of course that would be the galvanic battery, or however you want to deal with it. So I draw these in this context. You'll need 2 battery jars, and we'll put this is simplified in terms of for explanations and so forth, but they're not always set up as far as the materials go. But here we're going to have a solution of zinc sulfate, and we'll have a zinc bar in the zinc sulfate. I call it the common ion salt. Your text doesn't define it like that, but for memory purposes, the zinc will go into zinc sulfate. Then you'll have copper bar in the copper sulfate, which would be on the other side. You'll have a copper sulfate solution on the other side, and a copper bar over here, like that. And so that's copper solid and zinc solid right there. You will have connecting these two is a salt bridge. Salt bridge is typically a gel with embedded ionic compound, some kind of salt, something like sodium chloride, potassium chloride, a salt which will function to balance charge, which I will show you in a few minutes. So now that is the battery that's ready to function. And so you connect your battery to whatever device you're trying to operate, flashlight, and you light bulb, if you will, or run your watch, or in my case, hearing aids. And so these are button batteries, and I think I handed you out also, and I'll catch up with the rest of you later. you can see in there how the different reactions, the reactions are way different than what I'm about to use here and explain this. But the processes are still the same. You still have to have oxidation, reduction, and so forth. Well, in this process, zinc is undergoing oxidation. Here's our process up here, okay? And in the process, we've got zinc dissolving into solution, breaking down. And as it breaks down, it sends out cations. When a cation is delivered into solution, what does it leave behind? An excess of electrons. Because of oxidation. By the time we finish doing the several examples and working through this, hopefully that you'll begin to you get comfortable with this idea. Well, the opposite occurs on the other side. Oh, excess of electrons. That makes this electrode negative. And since it's undergoing oxidation, what do we call this? What kind of electrode is it? Anode? Yes, right. Anode. So over here, this will be the anode. Now, if you look back in your notes and you look at the electrolysis, you will see the anode is positive, etc. You can check that later on. So this is one of the examples where I try to emphasize use the process to define the electrode. And the other side is certainly opposite this. Here, copper undergoes reduction. See, you have copper plus 2 in solution. Well, if this is a load of extra electrons, that has to be released, so the electrons flow from the anode to the cathode. And so what's happening is the copper ions are removing electrons from the copper bar. And going to reduced form of copper. You're taking electrons out of that electrode. The copper bar is losing electrons. So if it's losing electrons, what's its charge? Plus. So now we have a plus electrode. So in this case, undergoing reduction, this would be, again, the cathode. And so the cathode is the positive electrode in a battery. Now, one of the things you want to check mark and keep in mind is that electron flow is always from the anode to the cathode. Check mark that 3 or 4 times. Okay, you build up on the negative side and you flow to the positive side. Charge flows from negative to positive, negative to positive, and this from the anode to the cathode. And this. One of the acronyms that I give people is ANO, a negative electrode oxidizing. ANO, a negative electrode oxidizing. ANO. So, and whatever's going on the other side is opposite that. So it's a cathode is positive and it's undergoing reduction, CPR. Okay, so either way, you can. CPR sounds like it's easier to remember. I don't know why I remember the ANO easier than CPR. But those will help you kind of keep your bookkeeping straight. And it's very important as we go through analysis on some of these that you be able to quickly pick out who's doing what at what electrode. Now, the only other thing in here that's missing is what's happening at the salt bridge. salt bridge is ionic compound, something like potassium chloride, sodium chloride. So I'm going to put a potassium chloride up here. I know it's getting kind of crowded. Sorry about that. As the zinc is oxidized into solution, that is, you're sending zinc ions into solution, that solution is increasing in positive charge. See what I'm saying? So as zinc is delivered into the solution, this electrode right here, the anode, is increasing in positive charge. On the other side, this is increasing in negative charge, because what's happening is copper is going to copper solid and it's falling out of solution. And so that's taking all the positives out, and so essentially this is leaving negative. Well, in order to balance the charge, that salt bridge in there will send their ions, salt ions, to the side needing a cation or anion. If I can find a color to show you this. Okay, if the zinc is building up a positive charge right here, then the chloride would be migrating into that solution. See? It's negative. So the chloride maintains a balance of charge. Okay? And same way with the potassium begins to migrate over to the other solution, and because it's becoming more negative, because you're losing your positive charges by precipitation of the copper. And so this has to, you just can't have this unbalance of charge in solutions. So the salt bridge is constantly sending cations and anions from salt into those solutions. So you have a balanced system, oxidation reduction system, and a sustained flow of electric charge. Okay. A lot's going on in there. My recommendation to you is practice drawing this out and use the copper zinc. It's the simplest one that I can give you, and how to deal with this. And identify the chemical process, the anodes, the terminology, and everything that's going on in the cell, because I'll be asking a number of questions that revolve around that idea. Okay? All right. Okay. Now we want to get into the analytical issues, analysis of galvanic process. Now for this, you will need your table of reduction potentials. We're going to pick the two. Notice all of the reactions that are listed as reduction reactions. We have in there we've got zinc plus 2 electrons going to zinc metal, and you have your reduction potential for zinc, and that's your standard reduction potential. I'll explain those later. But it's the amount of charge to stop a Wheatstone bridge. Everybody knows what a Wheatstone bridge is? Never mind. Okay. So you scan down here, and you find zinc, which is a minus 0.76 volts. So you got that down. And then you scan down, you find copper. I think it's on a positive, somewhere around 3. There it is. So you'll find copper, and it's also written as a reduction reaction, like this. And its reduction potential for copper is a plus 0.34 volts. Okay? Now, that's written in order of what's going on. Let's see, the minus 76. See, I've got, here's my zinc right here, and 3,4, here's my copper there. All All right, now just off of what I've told you in terms of what's doing what to whom, who's losing electrons? The one at the top. Who's gaining electrons? The one below. Because I've just told you, as you look at this, the electrons are going to flow from the more negative to the positive. Got it? That's all it is to it. So you have to treat the zinc reaction as an oxidation reaction. And then you treat the copper reaction as a reduction reaction. Electrons flow from top down on that chart. Top, down, from negatives to positives. So how do we deal with this in analysis? So this is the way the reduction table will come to you, like this. What you have to realize is the electron flow goes like that. So if you were going to describe a battery that's generated using these two reactions, the first thing you'd have to do is reverse the zinc reaction so that it shows zinc undergoing oxidation. And delivering its electrons out there. And copper does not change because you want it to show receiving electrons. That's aqueous. To reduce copper, like that. To simplify the analysis of this, do not change the sign of your electrode potential. So the electrode potential we're going to be talking about is still going to be a minus 0.76. And the electrode potential for, this is the way I teach it, okay? The book says something, it teaches it a little bit opposite. They say you turn a reaction around, you got to change the sign. Okay, well the equation I use simplifies this. I'll show you. But anyway, plus 0.34 volts. And so adding these together, as we've shown you originally, gives you the net cell reaction. Zinc plus copper goes to zinc ions. One of the conventions here is that when you write a reaction like this, put the ions close together, like that. And the reduced forms on the perimeters, or the outside, as shown here. Now there's another unique notation that you need to be aware of in writing these. Once you get this written, there is a notation that is written like this. It shows a separation. It's a parenthesis of brackets, and then two bars in the middle, which indicate the separation of the oxidation-reduction processes. And what you want to show is, on the left of the double bar, is the oxidation reactant and product. And so the oxidation starts with zinc and put a single bar and goes to zinc plus 2, like that. And then on the reduction side, you start with the copper ion, and so you write that down, copper ion, put a single bar, and it winds up with the reduced form of copper. That's a notation you need to get comfortable with. Oxidation, reduction. Now, oxidation reaction is first, and all this puts down. It doesn't balance the equations and all the other stuff. It doesn't put multiples in there. But what is in there that I haven't shown you yet is the concentration of ions generated. When the notation is written in this format, just as I've written it, you assume the ion concentrations in solution are 1 molar. That's called the standard cell. Okay? So in this form, assume zinc plus 2 concentration equals the copper plus 2 concentration, and it's 1.00 molar, and that's called the standard cell. Just a term, okay? But it implies the existence of a 1 molar. Excuse me. Over here, it's sending zinc ions into solution. Yes? And over here, copper is taking copper ions out of solution. Okay? What is designed for the start of a battery is in these solutions, you want to start with a very low concentration of whatever goes on the oxidation side. Concentration of oxidation ion. That in this case would be zinc. Because what you're doing is you're delivering more zinc into that side. And if you already have a load of it over there in that cell, well, you're not going to have any room to put any more. So, as it dissolves. So when you design your cell, the oxidation side of that battery starts out with a very, very low concentration of the oxidation ion. Okay, so this is a very low concentration of the oxidation ion, in this case, zinc. Okay, and on this side, you're going to be removing copper from the solution, so you want to start out with a high concentration of reduction ion. In this case, of course, here, because as the battery discharges, it's going to be taking that reduction side ion out. So you want to start out with lots and lots and lots and lots and lots of copper over here. Okay, because in time, it's going to decrease to 0, and what do we call that? Dead battery. That's the point. So you will see a process, and we'll get to this in, it's called voltage. And over time, you start out here with and your voltage will drop off like this until you get to 0, and you've got a dead battery. Well, in the course of discharging your battery, you have the oxidation side, or zinc, +2 concentration, way less than the copper concentration. At the start of your battery, you want a very, very low oxidation side. So now you start your battery, you connect your battery, you start throwing zinc into the solution, and start taking copper out of the solution. So the concentration of your zinc goes up while the copper goes down. So you might want to start with a 0.001 molar zinc solution against a 1.5 molar copper solution, so that the copper will come down and the zinc will go up, and your battery will be continuously discharging and flowing electronic charge. This making sense? Okay. So when you write the notation that I'm trying to share with you up here, and I'm really disappointed in that they didn't show it, but it'll show up like this on test day. What you will have is, say, zinc, single bar, zinc ions, and what they'll do is they put in parentheses here, parentheses, not brackets, parentheses here, whatever that concentration is at that given time. And then they'll bar it here, and then they put the copper and 1.5 molar, and bar that and put copper solid. See what I'm saying? So these two are not always one. Where are they one? If this is going up, if the zinc concentration here's going up and that one's going down, what happens is at this point on this curve, you will have zinc 1 molar and copper 1 molar at a very specific point on that curve. Bless. And so for one instantaneous moment in time, you have the standard cell. And once you get below that, the issue reverses, and zinc concentrations are greater than copper concentrations until your battery dies. Okay, so your zinc is built up and your copper goes away and you've got a dead battery. Well, you can do this with any pair of reactions on that reduction potential page. Pick any two. I think I saw in one textbook, I don't think it's in this one, there's something like 600 and some odd combinations that you can use for batteries in here. And remember, in all these galvanic studies, everything's in pairs. And they're listed in reduction potential, and they move from negative to positive. So now you can build all kinds of batteries. Go crazy. Okay? So a lot in the design of how to separate the reactions, how to start at certain concentrations and on the anode side and the cathode side, and that's the research end of this. And it is a very intense and very big deal in industry. Okay, going back up here to our original analysis right here, we have this battery going on, and it's sending electrons from oxidation undergoing reduction. So the reduction side is your copper, and your oxidation side is the zinc. Okay? Everybody comfortable with all the chemistry notations? I know it looks messy. So, what's the voltage on this combination? Or in other words, what's your battery voltage? Is the question I'm asking. Well, to calculate a battery voltage, I know we'll put it right here. E cell, under standard conditions, would be from the tables, numbers, is E, listen to me, E reduction minus E oxidation. Listen, what have I said? Row you both. Reduction minus oxidation. Okay? Simply substitute the values that are from the table. You don't change any of the signage. This is why I don't like changing the signage. If you'll use this E reduction minus E oxidation, it minimizes the number of changes that have to take place. Okay, so that you substitute and you change the signs and do whatever you have to do and make your calculation. So in the copper zinc battery, the reduction side is plus 0.34 volts minus 0.76 volts, and I think that's 1.10 volts. There's your cell potential for that combination. E cell, for a spontaneous process, must always come out positive. E cell must always come out positive. If it comes out negative, you're working with electrolysis. That's another world. Or you've got your oxidation reduction in the wrong place in your calculation. Are we kind of still with me? Okay, so the idea here is E, row you boat. E reduction minus E oxidation, pull the numbers right off the table, stuff them in, and calculate your standard electrode potential. Okay? When you do that, when you calculate your standard electrode potential, what you're calculating is this one right here, when you have 1 molar relationship in the flow of charge and all that stuff. So it is assumed when you do that E reduction minus E oxidation that your number you get is at standard conditions. Okay? How often or how long does it remain at standard conditions? Not long, guys. I'm just showing you what I'm saying here is that you start out with a low concentration on the oxidation side, a high concentration on the reduction side, plug up your battery, hook it up, and over time it'll go dead. Okay? And in some point in time in that process, you will have a 1 in 1 molar at 1 molar. The voltage above or below that standard potential line is simply said to be non-standard voltage. Yes? That's simple enough. So you're either at standard or non-standard. Well, you spend most of your life at non-standard. So we need to find out how to analyze non-standard voltage and figure that out. Okay. In the thermodynamic world of free energy, and we define these in terms of free energy, there is an equation that is used to define non-standard conditions. Remember, if we're at equilibrium, you have a K value stuck on the end. Okay? If you're not at equilibrium, what do you have? A Q value stuck on the end. So you've got to remember a little of this. Okay, so what I'm talking about, I can get my pen to work. What I'm saying is, in the world of thermodynamics, there is a delta G, I don't have the circle on it, this is non-standard, is equal to delta G circle plus RT ln of Q equilibrium. That's non-standard energy. If you get to standard conditions, delta G equals 0. So this term becomes a 0 equals delta G naught plus RT ln. What happens to Q at equilibrium? It becomes K value for that reaction. So you have your equilibrium constant. This is at standard conditions. And so this equation then changes to delta G equals minus RT ln K EQ, whatever you're working with. And we used this once before to determine the KSP of silver chloride. You will have that on the test also. You have to do that. And as a matter of fact, I think, wasn't that on the last exam? I don't know. In galvanic cells, delta G is the potential for doing work. Big numbers mean it's got a lot of potential for doing work. Little numbers means it does not. But when you talk about delta G, it is essentially the capacity to do work. How strong is your battery? Got a strong battery, stick your fingers on it and it'll blow your doors off. Okay? That's the issue. Okay? So the number G would be big boy. I mean, it'd be big kilojoules. Touch some of these that are dead, you'll have little bitty numbers. So that's where we're going. And some of this. So this is the capacity to do work. Well, work is W, and if you look in most textbooks, you'll find delta G equals work, which equals minus NF E naught cell. So that is if you have a standard cell. Well, we have 1-in-1 concentrations. You can calculate the delta G of your standard cell, and it is a minus NFE. Yes, you will have this problem on the exam. Calculate delta G naught for your copper zinc cell. Okay. Well, it's easy enough to do. Copper, excuse me, let's zinc plus copper plus 2 goes to zinc plus 2. And of course, if you're at the standard conditions, that's going to be an equilibrium. So you can throw in an equilibrium thing. and copper comes out of solution. So in oxidation reduction terms, what's going on? So we're starting at 0 and going to 2, plus 2, and then we're starting with plus 2 and going to 0. So you have a gain 2 electrons. Here's a loss 2 electrons. So what this means is that in this equation, N is the number of electrons being transferred in the oxidation reduction process. So N is equal to 2 in that equation. So it's the balanced oxidation reduction equation, and you will not always have, well, we'll get to it, these the same, like in this. I'll show you in a minute. F is your Faraday constant, and is 96,500 put coulombs. And trust me on this one. And the E naught cell is E reduction standard minus E oxidation, and we saw that at 0.34 volts minus 0.76 volts, and that came out as a net 1.10 volts. So we have the NFE for our equation up here. So does everybody understand the terms? Okay? So if I put that in here, I'm going to have a minus 2, 96,500 coulombs, capital C, and 1.10 volts. Volt times coulombs is joules. So this combination is now a minus 2 times 96,500 times 1.10 joules. So you see it's an energy number now. It's become an energy issue. So now, punching those in, we'll get joules, and you can convert it to kilojoules. It's a little more usable number. So we have the work for this is 212,300 joules, which is 212.3 kilojoules. So there is your free energy value for the copper zinc cell. Everybody okay on that? Not a complicated issue. But that is at equilibrium between the copper, zinc, and 1 molar, and it only lasts for a small amount of time. What you have to deal with is non-standard voltages on test day. So we go back to our thermodynamic equation. Delta G is equal to delta G standard of the reaction plus RT ln Q of the reaction. I'm just going to put RX of the oxidation reduction reaction. From the equation up here, this delta G equation that you used earlier, substitute this minus NFE into the delta G equation I have here. Well, delta G, non-standard. This is your non-standard right here. So it'll be a minus NFE cell. Notice it does not have this little circle on it. Non-standard. Then this side has a standard minus NFE naught cell. Yes, that's a reduction minus oxidation right off the table for that number. Please pay attention to me, guys. Okay, plus RT ln of the reaction ratio. Product concentration over reactant. Products over reactants concentration. If we were working with the zinc plus copper, it's not at standard conditions, going one way only, left to right. Zinc plus 2 plus your copper. You would have certain concentrations here, products over reactants, and these would be given in the problem. At this particular point in time, your concentration of zinc is 0.01, and your concentration of copper is 1.5. So what do you put in here? You put 1.5 over 0.001. If that's what, so you had copper starts out at 1.5 molar, and your zinc starts out at 0.001 molar, that's what you'd put in there. Because you're non-standard. The battery's fixing to deliver charge. You're not at equilibrium anymore. Q values are not at equilibrium. Which way will the reaction shift and stuff? Okay, so we have this set up. We're interested in and only in this term right here. Okay? So I'm going to divide through this equation by a minus NF number. Both are, well, only the F is a constant. I'm sorry. So divide through by the NF, and what happens is this becomes E cell, non-standard, is equal to a minus NF E naught cell over a minus NF. That's for the first term. I just divide through by the NF, plus RT over minus NF, right there, ln of products over reactant concentrations, like this. Well, that drops out real comfortably. These RT and F are constants. The only variable in here is, well, what N value will you have from the combination you choose? Okay, so this will reduce to this, equals E naught cell minus, see the minus down here, 0.0592 over N, believe it or not, log of products over reactants. I jumped over the log to, the ln to the log. Okay. Ln x equals, let's see now, log x, log x equals 2 point something, ln x, something like that. Anyway, we took that and substituted it. Okay, so it automatically comes out to that 0592. This is called the Nernst equation. For calculating non-standard cell potentials. Somewhere in the span of time for your battery, based upon the concentrations of oxidation reduction ions, you will have a cell potential. Now, we don't have an equation for the time frame, so the problems will come to you always giving you the products, concentrations, reactant concentrations, and you can, of course, you'll have the table, and you calculate all day long what the voltage would be under certain circumstances. So, let's calculate some battery charges. Okay, well, let's see what our system would be if we have the following. Well, we use the zinc. Zinc plus 2, 0.001 molar. And we have the going to copper plus 2, 1.5 molar. Sound effects are free. Anyway. Now you're also given the E naught zinc to equal a minus 0.76 volts, and E copper to be a plus 0.34 volts. And you know the electrons are going to flow from the negatives to the positives like that. So what do you need to calculate the voltage of this? Well, you of course need the Nernst equation here. So E cell non-standard is E naught cell minus 0.0592 over whatever the charge transfer is, log product concentration over reactant concentration. Well, of course, this is your reactant concentration over here, or your oxidation side. So you can have oxidation over reduction kind of thing if you want to do that. So we know that the E cell, we calculated this a couple of times, is 1.10 volts. Okay, 1.10 volts. All right, so that would go right here. All right, also in the zinc copper charge transfer, N will equal 2. Everybody okay on that? Okay. The product concentration is 1.5 and reactant concentration 0.001. So now you have all of the necessary data to plug in, punch it in your calculator, and you find out your non-standard potential. Comes out in volts. Okay, so here is 1.10 volts minus 0.0592 over 2 log. The product side is 1.5 over 0.001. Okay, so you have a numerical equation now, which you punch into your calculator and get an answer. So 1.5 divided by 0.001 equals that, and I'm going to hit the log button, times 0.0592 divided by 2 equals, okay, so I have 1.10 minus 0.094 volts. Okay, so it's, what I'm supposed to come out, wait a minute, let me run that one more time. 1.5 divided by 0.001 with the log button. Oh, yeah, okay. Okay, let me do that again. 1.5 divided by 0.001 equals that. 0.5 0.001 equals that. Hit the log button. Times 0.0592 divided by 2 equals 0.094. Okay. So you subtract that off of 1.1, and so for that combination, well, 1.1 minus 0.094 equals 1.006 volts is where you are with that combination. That's all it is to that. Okay. KEQs for galvanic reaction process. What's the extent of reaction for the zinc copper battery? Okay, well, we know that delta G equals delta G naught plus RT ln of Q. But at equilibrium, delta G equals 0. So I'm going to put that 0 right here in the front end of this equation. And Q will then be equal KEQ, whatever your equilibrium constant is. Because we're at equilibrium. So substituting that in, I have 0 to equal delta G naught plus RT RT ln of K equilibrium. And then this becomes delta G naught at standard conditions minus RT ln of K, whatever the equilibrium constant is. It can be a Kc value. Now, we know that delta G naught is a minus NF E naught cell. So if we put that into this equation, we have a minus NF E naught cell equal minus RT ln KEQ, like that. Divide through by the NF, and we have E naught cell to equal R minus RT over minus NF ln equilibrium constant, and this is 0.0592, becomes a plus, over N log KEQ. So here and here, you want to memorize that. Simply enough, all you have to deal with is, well, you got to get your potential right here, your voltage of your cell combination from your oxidation reduction, look at N, and then calculate KEQ. We'll do that for the copper zinc battery is E naught cell 1.10 volts, okay? So we've already done that one, and we know that N is equal to 2 for the electron transfer in the copper zinc. We've done this about 3 or 4 times. Everybody okay on this? Pretty straight? Okay, so using that, we just plug into E naught cell and solve for the KEQ. Like that. So that'd be 1.10 to equal 0.0592 over 2 log of whatever the EQ is. And so that's 2 times 1.10 over 0.0592 to equal log KEQ. And from the calculator, we can punch this into 37.2. And since it's a log, we're talking about base 10, so KEQ now, whatever it is, you can KC, if you're working with KSPs, whatever you want to work with. Here, you're defining equilibrium constant. Here, it would be 10 to the 37.2, so we have second 10 to the x. This is 1.45 times 10 to the 37. You think that's an efficient reaction? You bet. Everything's going to go until all the zinc's completely dissolved. Now, I've tried to give you an example. Everything's on the exam. Okay? You will have something as simple as what is the standard cell potential. Rho, just subtract the 2. You will have to calculate the potentials, non-standard potentials of the system that is, but the concentrations are not 1 molar. There is one problem that I want to emphasize here. Okay, this will be a non-standard cell potential in this. Calculate the non-standard cell potential for the following system: chrome plus 3, which is 1 times 10 to the minus 3 molar, double bar, and we're going to nickel plus 2, 1.5 molar. A single bar to nickel reduced solid. There's your reaction. Calculate the non-standard. You need non-standard cell potential. What you need is the equation. Why? Because the ratio of Q has to be raised to the coefficient power. They're not all ones. So thank you. When you look at this, what you have, chrome plus the nickel plus 2 goes to the chrome plus 3 plus the nickel. So in oxidation reduction, you got this and this. So you're going from a +2 to 0, and from a 0 to +3. So what is this? This is a lost 3 electrons. This is gain 2 electrons. Well, is this balanced by charge? No. Okay, so what I'm going to do is I'm going to multiply this first one by 3 and the second one by 2. So now, balancing this, I'm going to have a 3 here, and of course I'm going to get 3 moles of nickel precipitating out, and then I'm going to have a 2 here and a 2 in front of chrome, like that. Did you follow what I did here? All I did was just balance the charge and mass. Any questions? Okay. Then you'll use we can look up the values for nickel and chrome, E for chrome and E0 for nickel from our reduction potential table. So chrome will be above, there it is, a minus 0.74, and nickel will be below that and has a minus 0.23 volts. Okay? And so your E0 cell is E reduction minus E oxidation. Well, this is the oxidation end, and this is the reduction end. Remember, from negative to more positive. Even if they're both negative, you still flow from the more negative to the more positive. So this would be a minus 0.74 minus, no, reduction side, sorry. That'll be a minus 0.23 volts minus a minus 0.74 volts. So you add those two together, or no, subtract 23 out of it, excuse me. So what does that give us? 0.74 minus 0.23, 0.51, 0.51 volts. So there's your standard cell potential. Okay? So the E non-standard for the chrome nickel system is E0 for your chrome nickel system minus 0.0592 over N, not 2, N log of products over reactants. Well, your reaction says chrome is your product side. So you would want the concentration of chrome, but notice the coefficient is 2. So you want to square whatever you have put in that bracket. And for nickel, plus 2, you cube it. So the point here is it's the same as what we did a while ago for the zinc and copper, except you've got to put the reaction together and determine what your balance is so you can raise the concentrations to the appropriate exponential power. And as we always have in equilibrium. So to solve this one is 0.51 volts. 0.0592 over 6. Everybody catch that? Over 6? See, this is N equals 6. Okay, everybody good? All right, so log, all right, my chrome is 1 times 10 to the minus 3 squared over nickel, which is 1.5. I think that's cubed. And so, off you go with the calculator. Everybody good? Okay. I think I know, that's why I was uncomfortable. I had in the zinc copper calculation that we did, I had them on the wrong side of the ratio. Fix that. This is you do the zinc plus copper goes to zinc plus copper 0.001, see here, and 1.5. So please go back and check that in your notes. I'm sorry, my bad. Senior moment. So that should have been right here 1.10 minus 0.0592 over 2 log 0.001 over 1.5. The reason I got that, this should have been a positive when it finished with it. And sorry. Process of growing, I guess, growing older. Okay, so check that and run this one out, and you will officially be smarter than me.